Hi everybody, it's Mr. Woodward. In this video, I want to capture some of the patterns that we are starting to see among voltage, current, resistance, and power for both series and parallel circuits. So at this point, we've done a number of laboratory investigations, and we might be starting to see how these different quantities sort of work in the different types of circuits, right? Series and parallel. So I first of all drawn on the left side series circuit examples, 4 series circuit examples, and then I've drawn on the right side 4 parallel circuit examples all the way down. And I'm going to use these examples to illustrate some of the patterns that I'm talking about. Okay, so first let's start with patterns of voltage for series circuits. So let's assume that we have a series circuit with 3 resistors, and that these resistors are providing different amounts of resistance. Okay, so it could be 3 dissimilar light bulbs. It could be maybe here is like a refrigerator, and then a speaker, and then a microwave. Okay, any 3 things that provide resistance, and their resistance is not going to be the same as each other. Well, what we would find is this: if we were connecting these things to a voltage source, and I'm just going to use a really simple example, let's say a 6-volt source, okay? Then we would expect to see something like this. We would expect to see a loss of voltage across the first resistor, and let's say that it's a loss of 3 volts, okay? And then as we move to the second resistor, we might expect to see a loss of another amount, say 2 volts, and then the loss of another amount, maybe 1 volt. Okay, and those can be in any particular order. So actually, this example might even help to illustrate. It doesn't necessarily have to go down like that. This could be the 3-volt loss. This could be the 1-volt loss. This could be the 2-volt loss. Okay, but the point is this: here at the battery, there's 6 volts that's available, right? It's being provided to the whole circuit, and so that would be like an increase of 6 volts. Where those electrons are getting energized. And then of those 6 volts, 2 of them are being used here at the first resistor, 1 is being used at the second resistor, 3 is being used at the third resistor. And so we see this pattern that the sum of the voltage losses, 2, 1, and 3, is equal to the voltage gain at the battery of 6. Okay, and this is called the loop rule. Okay, so I'm going to write that up here, the loop rule, which is that the sum of voltages around any loop, and what I mean by a loop, right, is that this is a loop, okay, is equal to 0. The sum of the voltages around any loop. So in this loop, right, we're gaining 6 here, so we would have positive 6 plus -2 plus -1 plus -3 equals 0. Okay, and you would expect to see that around any closed loop in a circuit. Okay, the sum of the voltages is equal to 0 around any loop. Okay, well, what about in a parallel circuit? Okay, what patterns of voltages would we expect to see there? Well, the loop rule still applies. So the sum of voltages around any loop is still 0. But now the loops would be like this. Well, here, this would be the first loop, right? And then the second loop would be here. And then the third loop would be here. So we have like an inner, middle, and outer loop, okay? And so that means I would expect to see this. If this is gaining 6 volts at the battery, then I would expect to see a loss of 6 volts here, a loss of 6 volts here, and a loss of 6 volts there across each one, right? Because each of them is all by itself in a loop. And so with only one resistor in each loop, then that voltage loss at each resistor would have to be equal to the voltage gain at the battery. All right, so that's the loop rule for series and parallel circuits. The loop rule applies to voltage. And I should probably just say again, this is still called the loop rule, right? Sum of voltages around any loop is 0. Okay. Let's talk about current. What would we expect to see in current? So we've got these 3 resistors again. And if I were to take an ammeter and measure the current at various points, and I'm going to change colors here, let's go to pink. Let's say the current through the battery is 10 amps. Well, then if I could measure the current through the first resistor, I would measure 10 amps. The second resistor, I would measure 10 amps. And the third resistor, I would measure 10 amps, even though their resistances are different. Okay, that is to say that the current is the same everywhere in a series circuit. And so maybe I could write that like this, that the current at the battery is going to be equal to the current across the first resistor and equal to the current across the second resistor and equal to the current across the third resistor. And that would continue, right? If there's 100 resistors, they would all get the same current, which is the current that's flowing through the battery. All right, what if we're in parallel though? So let's say that I've still got 10 amps flowing through this battery. Now I would start to see something different. So I'm going to start with the resistor on the outside. So flowing down through this resistor, let's say that there were 2 amps of resistance flowing through that, and then let's say that there were 5 amps of resistance flowing through this one, and then there were 3 amps of sorry, I said 5 amps of resistance. I meant 5 amps of current and then 3 amps of current flowing through those. Notice that these currents, 2, 5, and 3, add up to 10, okay? If I were to go a little bit deeper, I could actually identify the current flowing through the specific parts of the circuit. So through this section, I would expect to see 2 amps, the same as here. Through this section, I would expect to see 2 plus 5, or 7 amps flowing through there. And then through this section, I would expect to see the 7 plus 3, or 10 amps flowing through there. Okay, and similarly through here, I would expect to see 2 amps. Through here, I would expect to see 5 plus 2, 7 amps. And then through here, I would expect to see 7 plus 3, 10 amps flowing through there. Okay, and the idea here is that at every junction, and I'm going to define this as a junction, so I'm going to go to red, this is a junction, right? At every junction, the current that's flowing in this case 10 amps, is equal to the current that's flowing out, which would be 7 plus 3. Let's take a look at another junction. So what about, I thought that might not work. Let me change colors to this one. What about this junction here, right? Well, now the current flowing in is 7 amps, and the current flowing out is 2 and 5. Okay, so this is the junction rule. The sum of the currents at any junction is now equal to 0. The sum of the currents at any junction is 0. Right, so again, with the green dot, right, we've got 7 amps coming in, but then we have a total of 7 amps coming out, so that the total current flowing in and out is equal to 0. You could think of this flowing into the junction as like maybe -7, and then this would be like +2 going out, +5 going out. Actually, it might make more sense the other way, right? If something's flowing in, that would be a current coming in and then losing sort of these 2 currents on the way out. So the sum of current at any junction is going to be equal to 0. Okay, we can't gain more current at a specific junction than we lose. All right, so those are rules for voltage and current so far, and I'll come back with resistance and power in the next video.